Well, hello, everybody. Welcome to the Museum of Science's MOS Live programs. Today, we've got a very special treat for you as part of National Chemistry Week. We have two chemists from the Massachusetts Institute of Technology who are actually going to share a little bit about what they do and show you actual chemistry experiments right here over our channel. Before we get started, I want to let you know that if you need closed captioning, you can just hit the closed captioning button at the bottom of your screen. If you'd like to ask questions or respond to some of the questions from our special guests, please do so in the chat and I'll be relaying those to them. And finally, if you are joining us on Facebook Live or one of the other media, unfortunately, we aren't able to see chat input from those platforms, but we're very grateful that you're joining us today. So at this point, I'm going to ask our two special guests to unmute themselves, to turn on their cameras. They're going to tell you a little bit about themselves and then get going with the science.
Hi everyone, my name is Giselle and I'm a second-year chemistry grad student at MIT. I'm in the Drennan lab where I study protein structure and function and solve the structures of enzymes so that we can understand the chemistry that they do.
Hi everyone, I'm Charlotte. I am a third-year graduate student at MIT. I'm in the Penality group and I study drug delivery. So using different compounds and structures to try and get drugs like cancer drugs into cells and into the brain. And today we're going to talk a little bit about solubility and specifically the concepts of like dissolves like. So if you guys have heard the term solubility before, could you let me know in the chat? And if you want, provide a potential definition. So what do you think solubility means? Or what does it mean for something to be soluble?
And while we're waiting for those answers to come in, Charlotte, do you mind also spelling it?
Oh, sure thing. So solubility is spelled S-O-L-U-B-I-L-I-T-Y, and soluble, S-O-L-U-B-I-L-E.
Thank you.
B-L-E.
I always like to give a few different points of access for people. All right, we're starting to get some ideas in from M. Reitman. We have dissolvability. Colin Kinsella says the ability to be dissolved. Looks like there might be some other things coming in, but if you want to continue, I can.
Yeah, so let's talk a little bit more about that. So like most chemists, one of my favorite molecules is caffeine, and 1 p.m. is the perfect time for a cup of tea. So when we think about solubility, it is, like I believe one of you said, the ability of something to be dissolved. We often think about it in terms of liquids, right? So the ability of the compounds inside these tea leaves to be dissolved into my hot water. So you can see the water started off clear and is slowly turning brown. That's because molecules from the tea leaves, such as my favorite caffeine, are slowly dissolving into that hot water. And if I want to make a great cup of tea, which I always do, I can add a spoonful of sugar, and we can see that slowly dissolve as we stir. And that sugar dissolves right in there. And I can add a splash of milk, and we can see that mixing its way through into the teapot. But one thing to note, although we're getting molecules from the tea leaves into that liquid, the tea leaves themselves are still solid and very gross. And so this brings us to some of our other concepts. A lot of things are soluble in water, and that's the main thing we think of when we think about things like dissolvability. But those tea leaves are still staying solid, and there are other things that aren't necessarily soluble in water. And so I just showed you my #1 favorite molecule, caffeine, but one of my favorite foods is a good stick of chewing gum. And so when we look at this just unchewed stick of gum, what are some things we observe about it? Can you tell me in the chat some of the properties of an unchewed stick of gum?
All right, I'm waiting with bated breath to see what the audience thinks. Properties of a stick of gum. It's been so long since I've chewed gum, I'm having a hard time. All right, from Karen, it's green. Poppy says
You're right.
It's solid.
Mm-hmm.
Vivian just thinks it's gross.
I'm insulted, Vivian.
Ryan also says solid. Let me see if we get one or two more. I think they're typing as fast as they can. Caleb says it's hard, but Connor says it's soft. Vivian really doesn't like gum. Okay, I think we got everything we're gonna do.
So You're right. It is both hard and soft, and it's also brittle, right? Very breakable. But I'm going to now break the cardinal rule of Zoom and chew very loudly and obnoxiously on camera. And let's see where this hard but kind of soft brittle solid goes. Nang, nang, nang. And we always say, don't try this at home. And I mean it because I am currently chewing with my mouth open on camera. But before I do the rest of my experiment, safety first, going to put on some goggles and a lab coat, partially because I don't want to get gum on my shirt. All right, so that's all chewed. I'm now going to do something even grosser and a little upsetting to me personally, and take that chewed gum out of my mouth. Now, how have the properties of this gum changed? Can somebody tell me in the chat some properties of a chewed stick of gum?
All right, so yeah, I'm looking for the properties of a chewed stick of gum. Benjamin says it's become softer. M. Reitman says elastic. Poppy says it's stringy. We got stretchy, whiter, stretchy,
Yeah.
sticky, slimy, and Vivian still just thinks it's gross.
Vivian's right at this point. Chewed gum, very gross. So you're right. Now that gum has gone from brittle to soft, smooth, and stretchy. Now some of that is the heat of my mouth warming and softening that gum. Some of it is the act of chewing. By working saliva in there, I'm starting to dissolve some components of the gum. So unfortunately, there's no way for you guys to get this through Zoom, but this gum tastes minty fresh now. And that's because the mint flavoring in the gum is starting to dissolve in my saliva. As saliva works its way into the gum, it's starting to allow the polymers that make up that gum base to stretch and slide against each other. So we've established the minty flavoring is soluble in water, but the gum is still staying solid in my mouth. So what might gum be soluble in, if not saliva? Give me some answers in the chat.
All right, so we're looking for what can a gum be dissolved in other than saliva? What do we think, folks? I know a lot of you have experience with dissolving gum. Joey says water. Karen isn't sure. That's a good answer, Karen. If you're not sure,
Great
you can
answer.
always say that in science. Laura thinks hot water. Poppy says shampoo. We got vinegar from Karen. Vivian is just still grossed out by this whole thing. M. Reitman says oil. Rubbing alcohol from Ryan. Does that give you enough to work with, Charlotte?
It sure does. All right, so I've got a mortar and pestle here. So I'll do some grinding and show you. So let's start with that vinegar suggestion. That's a good thing. Maybe some of the acid in the vinegar might break some of those bonds and solubilize the gum. So took some of that chewed gum from my mouth. Gonna put it in this mortar and pestle. I'm gonna add a splash of this apple cider vinegar. Good thing I'm doing this experiment in my kitchen, right? And so you can see in that mortar and pestle, now it's doubly gross. And I'm just gonna grind at it a bit. So I'm grinding away and I'm not seeing any changes in that gum. It's still sort of a gross, sticky green mess inside of that vinegar. Now, I know another suggestion was oil. So I'm gonna add a bit of oil here. And grind away. And here we are starting to see some changes in that gum. Most notably, the fact that I can't get it off my pestle now. But if I were to show it to you, you can see it's sort of a little stringier, a little different. And so that oil gives us a good segue, and the need for a paper towel, into some other things that might dissolve this gum. Now, as a chemist, of course, I always have caffeine around. I also always have a little bit of chocolate around my house, you know, for those days. And so I'm going to take this Hershey's Kiss. I'm going to put it on, not my mortar and pestle this time, but a cutting board. I'm going to just going to cut a little piece off that chocolate, being very careful with my safety goggles on. And what I'm going to do now is try to mix the two. Now, tell me in the chat, would we think that gum would be soluble in chocolate? Do we really think of solubility as a thing that solids have?
All right. While I'm waiting for that, I can tell you that several people approved of the chocolate on its own. But
Excellent choice.
so far, everybody's, let's see, we've got a couple votes for no, a maybe, a yes, a no. I'd say the no's mostly have it.
And I would originally have agreed. So I'm doing this on a cutting board now, and you can watch the gum kind of work its way into the chocolate. I'm gonna do a little more grinding down here where I can get easier muscle access. But again, here we're starting to see that gum working its way into the chocolate. And now I'm gonna keep grinding down on my cutting board until I get something, to be honest, as somebody who hates mint chocolate, that's kind of gross. Now, this is an experiment you can do at home if you take a piece of chocolate and a piece of gum and chew them together in your mouth. And so I've been doing this on the mortar and pestle, and you can see what I've created basically just looks like chocolate, right? We're seeing it's got the color of chocolate, it's got maybe the texture of chocolate, but it's got some of the elasticity. If I work it up in my hands a little more, now I've created this compound with the looks of chocolate, but some of the elasticity of gum. And so what I've done here is actually dissolved that gum in the chocolate. If you were to put this in your mouth, it would taste disgusting, but also it would have a texture sort of in between that of the gum and the chocolate. Now, this is all very interesting and sort of a theoretical scientific standpoint, which of course is my favorite standpoint, but there are some practical uses for being able to dissolve gum as well. And so I don't know about the other people with long hair, but one of my biggest fears as somebody who loves gum has always been getting a little bit of gum in my hair. And so here's when the real don't try this at home starts. Because I'm going to take this piece of chewed gum and I'm just going to get it right up in my hair. Just really work it in there. Because I know a lot about solubility, and now you guys do too. And so if I wanted to get this gum out of my hair, I would need to find something that this gum could be soluble in so that I can remove it from my hair. So you've all heard about different ways you can get gum out of your hair potentially. Maybe put some of those in the chat. Please save my hair and tell me how I can get this gum out.
All right, I got to tell you off the bat that several people have joined Vivian in deciding that this is gross, but we're starting to get some ideas in. Okay,
I'm also a little grossed out.
We've got ice, we've got water. A bunch of people are suggesting you just cut your hair off, but I think we're going to try to salvage it here. Oh, here's an interesting, here's the sign of the time. Wipes, presumably those little disinfecting wipes.
Oh, there we go.
Detangling spray, whatever that is. Oh, peanut butter. Freeze it.
Freeze it, yeah, the freeze it one's pretty common. So there's a couple different things. The freeze it there acts on actually not solubility, but the principle of what's called the glass point. So if you freeze things cold enough, they become brittle, and then you can break them like ice. But today, since we're talking about solubility, I'm going to try that peanut butter trick, but I want whoever suggested freezing to know that one does also work. And so you thought this was gross before. Let me show you peanut butter hair. So I got this peanut butter on my spoon, and I'm now going to work it into that gum. Trust me, this is just as gross for me as it is for you. But what I'm seeing is solubility in action. So as I work the peanut butter through my hair, I'm able, you can see the gum is sort of changing its properties. Now it's this smoother, disgusting substance that I can pull right out of my hair. Now my hair is currently instead full of peanut butter. And is that much better? I don't know. I will tell you, I tried this demonstration earlier and my pillow does smell like peanut butter, but it's actually pretty easy now that I've gotten most of the gum out to just dip it in some water and wash that peanut butter right out too. And so there we have a practical demonstration of the concepts of solubility and like dissolves like. Because we weren't able to dissolve that gum in water, but we could dissolve it in both chocolate and, luckily for me, peanut butter. Are there any questions about solubility and the gum and chocolate demonstration?
We have one from Caleb who asked, would the chocolate stick in water? I think probably wondering if the chocolate would make water stickier. That's my interpretation.
So chocolate is interesting. Some of the components of chocolate can dissolve in water, like you've seen in hot chocolate, and depending on what kind of chocolate you have, some can't. We tend to think of chocolate as something that sort of dissolves right into water, but usually what's happening instead is in hot water, when you're making your hot chocolate, your chocolate is melting. So chocolate has a melting point that's just a little bit above room temperature. Actually, right around 37 degrees Celsius, the temperature of your mouth, which is why chocolate just melts right on your tongue. So chocolate can somewhat dissolve in water.
Well, that's all the questions I see. Oh, nope, yours. Well, Poppy's asking, why did you purposely put gum in your hair? But that's all for science. And I think probably the rest of them are in the kitchen doing that as we speak. So thank you so much, Charlotte. I think you got it all.
Great. And now you've seen some examples of like dissolves like in action in the kitchen. And Giselle is here to show you some examples of like dissolves like with colors.
Hi, everyone. All right, so I'm going to do a tie-dye demo today to kind of illustrate the same principles of solubility and also to illustrate a really cool technique called chromatography. So Charlotte did an excellent job of explaining what solubility is, and we've learned from her demo that it is a measure, kind of a measure of how well something dissolves into something else. And as we see from Charlotte, that it doesn't just refer to a solution of a solid and a liquid, but it can refer to mixtures of liquids, mixtures of solids, or mixtures of gases even. And also, as we learned from Charlotte, one way to kind of think about and maybe predict solubility is to keep in mind the phrase like dissolves like. And so that means things with like similar chemical properties will mix well and dissolve easily together. So has anyone heard the word chromatography before? Have any ideas what that would be?
Right, chromatography. Any thoughts from our friends? Watching the Q&A with bated breath. All right, we got no. There's Vivian's got an interesting answer. Vivian is remembering Google Chrome and wondering if maybe there's a relation. Vivian's also thinking of cameras and photos. Sue Kunkel is saying the study of color.
Kind of. So you're sort of on the right track, but what I think of in chromatography is it's actually a laboratory technique that we use that takes advantage of the solubility of compounds to separate mixtures of things. And so that's a really broad definition, and it's because it kind of is a really broad technique. So in the lab, you can have things like liquid chromatography or gas chromatography. You can run it through a variety of systems like a column, a tube, a plate, lots of different things. But the overall concepts are the same. So you're going to have one compound or a mixture of compounds dissolved in something called that moves. So it's like a mobile phase. And then it's going to move through something that's stationary, and we call it the stationary phase, and carry those compounds along with it. And they're going to move through that. They're going to move through at different rates based on their solubility with the mobile phase and the interactions they have in the stationary phase. So if something is soluble in that phase that moves, we expect it to move quickly along with it. However, if it's not soluble, we expect it to stay in place. And so this is how we actually separate mixtures of things in the lab. And I do this all the time to separate mixtures of proteins. So what I'm going to do to illustrate this is a tie-dye. We're going to tie-dye masks together. So I have these two masks with drawings of DNA, which is just the most beautiful molecule. And I drew them with Sharpie markers, and this is something to keep in mind. So it's a permanent ink marker, and I just have it on a cup with a rubber band around it. And actually, before I start, safety first, I'm gonna put on some safety goggles so I don't get anything in my eyes. And if you wanna try any of this at home, make sure you wear goggles, make sure you have an adult present and everything. And so, in order to actually get these colors to run, to actually tie-dye them, I have two different choices of solvent. I have water and isopropyl alcohol or rubbing alcohol. So this is like what you can put on cuts to kind of disinfect them and everything. They sting a lot. Does anyone have like a hypothesis about which one might be the best thing to tie-dye with?
All right. What would be the best thing to tie-dye with? We have water from Anthony, also Karen, Kaylin, Marie. Sounds like we've got a lot of young hippies out there. Poppy says alcohol, so does Laura. More water, alcohol from Harrison, who's 5. So alcohol and water seem to be the big choices.
That's great. Yeah. Well, let's test those hypotheses. Let's see what's up. I'm going to do water first. So I just have it in a dropper right here, and I'm just going to saturate, get the top of this all wet. Bear with me. All right. Can you kind of see what's going on? All right, does anyone want to type any observations they have as we're going throughout this? Does anyone see anything that's happening?
Okay. Any changes happening? All right, Karen says it's shiny.
A little bit, yeah.
Vivian says not much of an effect. Poppy says sort of dyed.
Yeah, it looks a little darker because everything is wet now.
But
I
got to go to one. Marie says the purple has melted.
I think I just drew it really thick. I messed up a little bit when I was drawing it. But yeah, these are all great observations. But overall, it doesn't seem like there's much going on. It's a little darker. Maybe it's spread a little bit. But overall, not much. So what can we kind of think about? I guess let's try the one with isopropyl alcohol, and then we can compare both observations. All right, so let's do the alcohol, and let's start on those colored bands in the middle. Oh, wow. Does anyone see anything starting to happen?
Okay, Vivian says it's spreading. So does Laura.
Yeah. Check it out.
Marie says, yep. It's mixing, it's spreading from Zoe. M. Reitman says the color's bleeding through. It looks like highlights from Anthony. Vivian really wants you not to hurt yourself. Okay.
I won't hurt myself, don't worry.
The color's bleeding.
You guys are all right. So compared to our water sample and our isopropyl alcohol sample, what are the differences between each? And what do you guys think that means?
All right, looking for differences between the samples. The water seems to be weaker, the alcohol is stronger. And mostly it's things like cool.
Yeah, it is really cool. So yeah, that's completely right. We can see that the alcohol is actually moving the pigments, the ink, through our mask. So if we think back to our chromatography example, the alcohol is what we would call like our mobile phase, the phase that's moving, and the mask is the stationary phase, what's just staying put. And we can see that the alcohol is taking the ink and moving it through the mask. So we can kind of deduce that the ink from these Sharpies is soluble in the alcohol, but not in the water. Because in our water sample, the inks just stay in place. They're not really moving with the water at all. And so the ink and the alcohol kind of must have similar chemical properties to them. And let's see. So if you're going to tie dye at home, if you're going to use Sharpie ink, which is, permanent marker ink, you'll want to use the isopropyl alcohol. What other observations can you guys notice? Here, let me hold it up a little closer.
Harrison says the alcohol one looks like a rainbow.
Yeah, it kind of does. So that's a really good point. And if you guys look at the black, and I'll show other examples to kind of illustrate this a little clearer, is the black doesn't seem to just be made of black, right? Which is kind of interesting to note because you think, well, it's black ink, it should just be made out of black. But something that is really cool with this experiment is that we can observe that some colored inks are not actually are made of multiple colors. And then this technique helps us to separate all of the different colors that were mixed in to make that one ink. So to kind of see that a little bit further, this is one I dyed a few days ago. And so it has had more time to spread out. And you can see that the black kind of fades to purple. And so the black is made of mixing purple inks and other inks. And to also show this a little bit further, I did it on some paper towels, which are even easier to see than the masks because things are just moving, straight up and down instead of kind of over the curves of the mask. And so I did it in a few different colors because if we kind of think back to like when we were in school and mixing the primary colors, black's probably not the only color that could be mixed, have different colors in it. So my favorite one, the purple ink right here, you can see is actually made up of like red inks, and then it's a little hard to see here, but blue ink in the bottom. And this is just, I took paper towel and scribbled the marker at the bottom and then dipped it into the alcohol and let it spread up. And this is something you could also do at home. You could try a bunch of different kinds of markers. You could try different solvents, alcohol, water. You could try soda, see what works. If you have an adult and some safety goggles present, even if you don't have masks, this is a really cool thing to try. And with green, that's another color that you can see separate into multiple colors. So we can see yellow, and then it's kind of hard to see on the camera, but there is a little bit of blue at the bottom. And then blue, it actually isn't full of a mix of colors. It's just one right there. And then here's the black, which is a little harder to see on the masks, but we can see that it separates into this purpley pink. There's some blue down there, and then a little bit of red too as well. And this is actually ballpoint pen ink, so it's not a Sharpie at all. So we can see the same color change that happens again. So do you guys think that if I used like Crayola markers, do you think that the same thing would happen? Or do you think it has to be like a specific type of ink to have this effect?
Vivian says, no, it shouldn't matter. Lexi thinks it has to be specific. Debatable, all kinds of markers, so all over the place.
Yeah, I mean, this would be a cool thing for you guys to try out at home. It could, for a water-soluble ink like a Crayola marker, I mean, we would see it probably run in water, but maybe we'd see something else different happen in the alcohol. However, for these Sharpies, we see that it doesn't run up in water, it only runs up in the alcohol. And so these are all really good hypotheses that you guys have made, and definitely fun things to try out. Does anyone else have any questions about solubility or about chromatography like this?
Thank you, Giselle. We've got a couple stacked up. Caleb asked a couple. Let's go with this one. Caleb noticed that the purple one seemed to melt the most. Do you have any thoughts on why that happened?
I mean, let's see. It could just be because I scribbled a lot of it on there, but also maybe, yeah, it's probably just me scribbling it harder than the rest. But it could be made of a different mix of colors. So the pigments used in the purple ink could be slightly more soluble in the alcohol and move faster than like the pigments in the blue or the green. That's a really good observation.
Okay, cool. And Karen earlier mentioned apple juice. This is, I know, something they could try at home, but how is apple juice closer to water, closer to alcohol? Is it something different?
I would say apple juice would probably be closer to water because we think, I guess when you think of it and when you drink it, you notice that, well, it kind of has the same viscosity as water, but it's sweet and it has some other things. So apple juice is primarily water, but it also has a lot of dissolved sugar in it, and then also flavor components from the apples and various vitamins and minerals. So my hypothesis, it would be most like the water itself. However, because of you have all that dissolved sugar and those minerals and vitamins in there, they might mess things up a little bit. But that would be really interesting to try out.
Okay. I don't see any other questions, but I think we've got a great thing to end on. Eljo writes, bye, my class ends right now, but this was fun. And it really was enjoyable. So at this point, I'd like to invite both of our extraordinary special guests from MIT to pop their cameras on and just say goodbye to everybody.
Bye.
Goodbye.
Thank you for joining us today and sharing those wonderful experiments. I'm hoping there'll be lots of children with gum in their hair and tie-dyes on their shirts today. And for all of you at home, thank you so much for joining us today for Science in Action. Remember that we've got other activities this week as part of the National Chemistry Week. You can see all our virtual offerings at mos.org/MOS at home. You can always support us by going to engage.mos.org/welcome. And just a reminder that all these activities are made possible by a generous grant from the National Science Foundation. Thank you so much for joining us at the MOS at Home. Have a great day.